Our next speaker is Dr. Alicia Caruso, and she joined the survey a few years ago after completing a PhD at Adelaide Uni. Her focus and interest in research is on using remote sensing for mineral exploration.
Okay, hi everyone. It truly is bright up here. We're going to talk about HyLogger and what the year we've had this year in 2024. As Bron discussed this morning, we've had a really successful year. Following a lot of work health and safety kind of improvements and changes in the lab, we've been able to develop or process and scan over 17,000 metres of core from all of these variety of internal GSSA projects. ISCG projects, preparing for the Northern Gawler NDI, ADI, and also with critical minerals. The drill holes we've scanned are across the state. All the red dots up there are drill holes we've scanned entirely or in part, and we'll be completing any of those incomplete, hopefully in 2025. So we're going to talk about data. One thing that Bron also mentioned this morning was our cache. There is now a National Virtual Core Library cache, which means that all of our HyLogger 1, 2 and 3 data from across the state is really easily accessible to you, the people who are after it, via this cache. The link is here. It will be on the slide for your viewing pleasure later. There's a lot of browser extensions you can use, whichever browser you prefer, to download all this data. We've got all the details in this photo at the bottom here and all your links, so you can download individual drill holes, or you can also download everything from the state with a browser extension. There's also data from across all of the National Virtual Core Library available at this link, so every state and territory is separated individually, and then you can download that as you please. So we're going to touch on a couple of case studies, 3 in particular, so from critical minerals in the southern Curnamona, the ISCG work, a little bit in the eastern Gawler, and also a few drill holes and some information from the Warburton Basin. So starting on critical minerals, this was supporting the GSSA Critical Minerals Project, so looking at Diana Zivak's work with the report book that's recently been released up there on the rare earth potential of SA, and primarily focusing in the southern Curnamona. This particular prospect is shown here in this red box, the Bulkamata GK1 occurrence. This is hosted within a biotite muscovite chiastolite schist, and there'd been previous geochemistry from the company back in the day that had shown significant phosphorus results. So this was something we were kind of interested in finding a little bit more out about. And when we were scrolling around with our HyLogger data, we hit bingo. Our photo in the middle there is showing the reference spectra in purple, and the spectra from the actual sample, which is in the top photo, in black, and those 4 arrows are the key things we're looking for when we're looking for monazite. Really excitingly, normally it's just a very small kind of feature, but these are very large, and these diagnostic features are huge, and it really encourages us that this is bingo, monazite. This was then sampled for geochronology, and so you can read Dee's report to find out more, and the photo in the bottom there is what it actually looked like in the end, full of monazite. Next, I'm going to talk a little bit briefly about some ISCG work that's happening. So this is a drill hole MGD56 from the Con Ryan prospect, just south of Emmy Bluff. An important aspect of understanding your ISCG prospect, I'm sure as we all know, is recognising your alteration mineralogy, which is really great and easy to do with the HyLogger. So we're able here to differentiate our case bar from our dominantly albite at the bottom of this section of the drill hole, which are visually really similar. You can see the photos on the right. They look quite similar, even though maybe one's stronger than the other. But when you reveal this information in the HyLogger data, you can see that we've got a change between potassic and sodic alteration. And within there, there's also quite a lot of chloride alteration. So we're able to map our downhole patterns in the mineralogy. So we've got increased white mica at the top of this drill hole, and then which is kind of linked with our higher bismuth results with the assay. And then there's a kind of a boundary with the white mica and the chlorite, where we also see our copper mineralisation and interest. So we can link our assay with our HyLogger data really nicely and link that back to the actual physical core and the assay itself. So touching on the Warburton Basin, which I mentioned before, this is some work with the Basin Prospectivity team that's kind of just started. We've recently scanned a number of drill holes, and I'm going to focus on 1 or 2 in this little section here. They're looking to revitalise gas exploration in this basin. It's got a lot of known potential, but very data poor. The aim is here to integrate the mineralogy earlier in the process. So there's obviously traditionally collected petrophysics, and the HyLogger is being collected to identify those spectral signatures of interest. This is ideally to help us facilitate and understand the lithologies and the stratigraphic interpretations and knowledge. So instead of having the traditional petrophysics and then linking to knowledge and then understanding of mineralogy, we're trying to put the mineralogy earlier into the process and understanding. of this kind of workflow. So there's a couple of ways we're going to touch on this. This is from a particular drill hole in the Warburton Basin. This whole tray is full of the Patchawarra Formation, a known major source rock for gas and oil in the Cooper Basin, and this looks the same. It all looks pretty consistent. But there is some spectral variation. If we dive a little bit deeper, we look at a couple of particular points. The point on the right is primarily well-crystalline kaolinite with potentially a little bit of dicite. We have our spectral signature here for that first star in the second row. And then on the left, we can see just in the next row, 10, 20, 30 centimetres away, we have this change where we have a really diagnostic dicite spectral signature with those two doublets. We have a really successful and positive match with our spectral assistant, with our software, and this is really encouraging. So maybe this is indicating there's a change, although it's on a small scale, maybe that's going to turn into something on a bigger scale. Work to come. So this is just a start. And another way we're going to utilise this, when it loads, we're looking here at a variety. It's very colourful, very exciting. So we have our shortwave infrared data from our drill hole from STIRT 8 at the bottom. We can see really clearly here there are 4 very unique spectral kind of mineralogical packages. When we look at our tray imagery, that's the plot just above, we can see it's all of our HyLogger imagery from all of the trays, all of the core rows stacked together. You can see there's kind of 4 kind of colours. And that actually relates to 2 specific formations that was all logged in the well completion report. Above that, we have actual photos from our HyLogger data from the imagery, and we can see that we have these clear 4 formations: conglomerate, the coal, the tuff, and the rhyolite. The interesting thing that I find that although there is obvious colour changes within the Murucuchi volcanics, we also see at the bottom that there are really obvious spectral changes. So we're going from kind of a clay white mica mix of some description into 2 kind of different types of white mica that are blended together throughout that section of the drill hole with the rhyolite versus what you see in the tuff. And then again, we also see different things with the conglomerate. There's kind of a variation between well-crystalline kaolinite and muscovite, and then they also change within that lithology. So these are some things to follow up. Of course, our coal is aspectral. It's black. We can't see a lot in our shortwave infrared, and because it's quite reflective and very low response, we also struggle a little bit in the thermal infrared with coal. But I feel like, in a way, a negative is also kind of a good thing. We can clearly see what's going on there. But the big exciting thing that's been happening really recently, and it's been taking a lot of my time, is, as Bron and Paul mentioned, the HyLogger 4. This is an exciting development. It's been many years in the making. We're really excited that it has finally arrived and it's been installed and it is working. It is currently the only one installed in the world that works. We're future-proofing our HyLogger 3 with this new machine. Spare parts are becoming difficult to source. Although our data is reliable, we do have some bulbs. Things are getting hard to find. So the advancements with the HyLogger 4 is we have our high-resolution imagery of 25 microns. We're now collecting mid-infrared data, so that's coupling with all of our vis-near SWIR and thermal infrared data. We're filling the gap that we've had with HyLogger 3. We've got an improved spectral resolution for the thermal infrared, and interestingly, I mean, kind of boring but exciting for me, we have improved storage, network, and internet access, which is very dull but is really exciting for our data management and how we're going to handle it all. We're also able to weigh every tray, which is an interesting tool that we're not sure how to use just yet. And we're also now collecting 3D profilometer data, so kind of like a LiDAR. And also it arrived in this very large crate, which people did make the joke on the day that they thought maybe it was that elephant that went to Monado Zoo. It was a very large, very tall crate. That's what the truck driver thought. It was very funny. But here it is, installed in the lab in the Waddle Laboratory at the Core Library. We've been able to successfully scan core trays, rock samples, and our test rocks that we scan on a regular basis, multiple times a day. It's a really exciting development. It's a very commercialised machine from CoreScan when CSIRO spun out and commercialised the HyLogger in 2017. And now, this should work. Here is it scanning. It works. It's amazing. It's exciting. We have, this is the scan head, so now the scan head will move to the tray and the tray will motor along. We have from right to left, we have our 3D laser profilometer, RGB camera, mid-wave and thermal infrared telescope, the longer one, and then we also have our spectrometer on the right, so our vis-near SWIR spectrometer on the right. So this is just the one row. It's very exciting, it does work, and it goes at this speed, which I think is really nice and really consistent. Are we finished? Yes, there we go. So we're going to look at some imagery, because that's kind of one of the big visual exciting things. This is our original raw imagery at the top, so it does come out quite dark, but even just a basic colour adjustment in your Windows photo app, you can see a significant, it really lights up. And from there, we're going to zoom in. So this is at 30% of that full core row. These are a couple of veins, and this is from the MSDP 11 drilling. We have a 2mm and a 5mm vein. You can already see there's quite a lot of detail in there, but we're going to zoom in again because we can. This is the full 100% zoom didn't actually fit on a slide, so this is most of that. But we can see clearly individual grains with this infill and alteration around these veins. You can see individual kind of minerals and things going on within the vein. And again, same veins, 2mm and 5mm in real life, and this is what they look like at most of the 100% zoom. So that's the raw imagery, but we're also still going to be using TSG. So this is a TSG tray image. It does have to be downsampled a little bit so that TSG can handle it, but still the quality is significantly better than what we've been currently achieving with HyLogger 3, which I'll demonstrate now. We're going to zoom in again on that same area. So this is from the tray. We're going into a floater window that's been zoomed in. It's not going to be quite as sharp and quite as amazing as the raw imagery, but I still think this is a great improvement when you compare it to this. It's not necessarily a perfect comparison, but there's also some colour differences, but generally we're seeing a little bit more fuzz. It's not quite as sharp, not quite as clear compared to our HyLogger 4 imagery. So we're quite pleased that we have this great advancement, and we're looking to see what we're going to do next with all of this work. One other thing is we're doing spectral comparisons with all of this, so scanning things like our test rocks, which is a known set of samples that we've scanned twice a day for many years. In this particular example, I'm just showing you the spectral features for quartz. We have very consistent, the actual signature itself between HyLogger 3 and 4 looks very much the same, which is really encouraging and really positive for us. There's a slight change in the mix from the spectral assistant unmixing, but both of these are all quartz, and it's really just which reference spectra it's used to unmix. But they're both quartz, which to me is a bit of a relief and really good. There's maybe a little bit of noise, but we're going to continue working and collaborating with the engineers and the software people at CoreScan to kind of continue developing thermal infrared, and also the HyLogger kind of machines are all really new to them. So we're looking forward to working with them in the next 6 to 12 months, and I expect the years beyond to kind of, work together and improve where we need, and be able to develop reliable, consistent products that we can provide to our stakeholders. So we'll be looking at other minerals, other rock samples, things like that into the future, which is leading me into what's next. So we're going to do about 6 months of testing, looking at well-characterised samples, assessing our data quality, like I mentioned, but that will also be with with legacy drill holes. We're going to test our new features like our tray weighing and our 3D profilometer, see what use case is kind of what we can do with that and how that's going to benefit our data collection and data delivery that we provide to people. We're going to also do legacy drill hole scanning, so from major deposits, but also filling in and kind of replacing all of our HyLogger 1 and 2 data. I actually was quite surprised with how much there was. I didn't realise we still had so much HyLogger 1 and 2 on SARIG, so we're looking to kind of turn that over and replace that with HyLogger 4, but potentially also some HyLogger 3 data depending on our roster next year. But our HyLogger 3 will be continuing. We're going to continue collecting data with a reliable machine that we still know, love and trust. And so we'll be looking to start off in December with our Northern Gawler NDI that Claire showed earlier. So we've got some chips and some core to scan, which is really exciting. And then we're also going to fill in some gaps in Eyre Peninsula. We find that there's actually a bit of a black hole in terms of HyLogger scanning on the Eyre Peninsula, so we're looking to kind of fill in some of those gaps, as well as do all the other things I've discussed. And then aside from the scanning, we're going to look at developing a sustainable chip workflow. So from the scanning to the processing, both ends of that kind of need to be sustainable and work in our environment. And so we're just looking to kind of reassess where we're at and come up with a product that then is still usable and great for people who are after those chips, that chip data. I'd just like to acknowledge a variety of people, our technicians, the lovely staff at the Core Library who've been really helpful with all of the changes we've been dealing with. Those at DEM facilities and our work health and safety people for this year. It's been a lot of stuff we've been doing. Those supporters from Epiroc, CoreScan and the HyLogging systems, so they help with us our maintenance and delivery and access for the machine. The Ozscope and the National Virtual Core Library, and those at SARO who support the MVCL through that. Thank you very much.